Last time we discussed how to write chiral superfields and analyze some of their properties. So one property we noticed was that F term of a chiral superfield F term is the coefficient of theta term, theta term. Chiral superfields were to be written as functions of y and theta, and the theta component of that chiral superfield we call an F term, or F term of a chiral superfield, or also an anti-chiral superfield. And that would be coefficient of theta bar term, because anti-chiral superfields would be written as functions of y bar and theta bar. They transform under SUSY by a total derivative. So if we want to construct a supersymmetric invariant Lagrangian, this could be a good candidate because it would transform under total derivative, and an action which is the Fourier integral of Lagrangian would be invariant. Then we also discussed that product of two chiral superfields, that's phi 1 function of y and theta, and times phi 2 function of y and theta, is also a chiral superfield. By construction, because product is also a function of y and theta only. And product of two anti-chiral superfields is an anti-chiral superfield. In fact, product of any number of chiral superfields is a chiral superfield. Product of any anti-chiral superfields is a superfield. 2, 3, 4, 5, whatever you want. Then we asked, what about a superfield which is a product of a chiral superfield, anti-chiral superfield? Is that how I wrote it? Yes. And a chiral superfield and anti-chiral superfield. Clearly, it's not a chiral superfield because a function of both y and y bar and theta bar is not a chiral superfield. But then we said this superfield, which is a product of two chiral and anti-chiral superfield, has an interesting term that we call D term, which is the coefficient of theta square and theta bar square. So, for example, if I write phi 1 dagger y bar theta to be phi 1 star plus root 2 theta psi 1 bar y bar plus theta bar f2 y bar star, because that would be a general expression for a anti-chiral superfield in terms of its components. Phi 1, a scalar field, psi bar, a fermion, and F2, the auxiliary field, F2 star. And phi 2 y theta will be phi 2 y plus root 2 theta psi 2 y plus theta theta F1 y. Now y bar was x mu minus I theta sigma mu theta bar, and y mu was x mu plus I theta sigma mu theta bar. So I could put these back into it and make an expansion of these objects. So 1 bar. And this expansion I think we wrote was phi 2, phi 1, x star, I theta sigma mu theta bar, d mu phi 1 star x minus 1/4 theta square theta bar square box phi 1 star where box is the shorthand for d mu plus root theta bar psi 1x plus I by root 2 theta square theta sigma d mu psi 1 x plus theta bar square f1 x star. Expand y bar as this and make a scalar expansion. This is 1. We wrote this expression earlier sometime. This is what it is. And similarly for phi 2, there's a plus I think here, conjugate of that. Minus d mu psi 2x sigma mu theta bar plus theta square f2x. And then let's construct the product superfield. There will be various terms, but let's isolate theta square, theta bar square term. Well, which is product of these two. So there is theta bar square here, there is theta here. So this is one term. F1 star F2. There is this term, which is theta square, theta bar square times phi 2. So minus 1/4 phi 2 box phi 1 star and similarly 1/4 phi1 box phi2 star. Something I put stars wrong, right? 1 is with stars and 2 is without stars. Then there is this term times this term. It has 2 theta's and 2 theta bars. So it's this square this. Use the phase rearrangements and you will get this out, and then plus half d mu phi 1 star d mu up phi 2. Is it plus sign? I think it's a plus sign. Now this is theta square term times the theta bar. Multiply that with this theta bar. So that becomes 2 thetas and 2 theta bars. Do phase rearrangement. You will get that plus or minus I by 2 d mu psi 1 bar sigma mu bar psi 2 plus I by 2 minus I by 2 psi 1 bar sigma bar mu d mu psi 2, all functions of x. And this term we call d term. That's naming. D term is the coefficient of theta square, theta bar square. And D term has the property that D term always transforms under SUSY by a total derivative. All right? You could check that because we know how these various fields transform and see how this whole thing transforms, the lengthy calculation. But you could even argue without doing calculation that has to be so by simply using dimensional arguments. What is the dimension of this D term in this superfield, this product superfield? What is the dimension of D term? Mass dimension? Here, in this superfield. This superfield, each one of them is mass dimension 1 because it starts with a scalar field of mass dimension 1. We prescribe that. So, this object is mass dimension 2. Each theta is mass dimension minus half. So, theta square is minus dimension minus 2. So, this has to be mass dimension 4. Now, if I make a supersymmetric transformation of this D, what does supersymmetry do? It converts the field into a mass dimension half larger than the field. So, I need something on the right hand side which is of mass dimension. So, mass dimension of is 4 plus half. But 4 plus half, that's it. So then, which means what I have here could be some epsilon times x which is mass dimension 4 plus half, or epsilon times some derivative of where m is mass dimension 3 plus half. So that this is 4 plus, derivative is 4 plus half. Now, a component of this superfield with mass dimension 4 plus half cannot be a component here, because the corresponding theta coefficients for that will be larger than theta square and theta bar square. But any power of theta larger than 2 is 0. So there cannot be this component, just by dimensional grounds and properties of superfields. So we are left then with a derivative of this object. That's a total divergence. Now what would be now in this superfield, because it has to be some component of this superfield, because supersymmetry must transform fields amongst themselves for a multiplier. So it would be some component of this with mass dimension 3 plus half. This is mass dimension 2. So some component here which is mass dimension of 3 plus half, which is 1.5 larger, is the coefficient of 3 theta term. Because 3 theta term will have mass dimension 3 plus half. So y is the coefficient of theta square theta bar or theta bar square theta term. Right? And by simple, right, it has to be fermionic. And because it has a mu hanging around, it has to be vector, which means it must have sigma mu sitting somewhere. And that's a total divergence. So this is a generic argument for any d term. The same way you could have argued for f term also of a chiral superfield, that it always will have to be transforming into total derivative. Is that clear? So now we can use this property also. We can.
Any d term under superfield transformation goes to the term coefficient of theta square theta.
Yes, derivative of coefficient of that.
It's always true.
It's always true. By simple dimensional arguments and completeness of the supermultiplate. So now what do we learn? We learn that if we want to write supersymmetric invariant actions, all we do is we cleverly find f terms of some chiral superfield and d terms of some general superfield. So let me start constructing now Lagrangians, supersymmetric Lagrangians. Take a set of chiral superfields, a set of chiral superfields phi I, which is a functions of y and theta only by definition because they are chiral superfields, and I could be some number 1, 2, 3, whatever you have. You can take any number of them. And then construct an anti-chiral superfield by conjugating this. Multiply by same I now. This product is a real product because it's self-conjugate. So this can be a term. Now this is not a chiral superfield, but if I take the D term of this object, that will be a real Lagrangian and will also transform under supersymmetric transformation as a total derivative. Done? So that's a candidate for supersymmetric Lagrangian. And it has the right dimensions the way we have constructed it, because D term of this superfield is dimension 4. This product superfield. So it has the right dimensions in 4 dimensions. Now, to this, I can write a polynomial of chiral superfields. One superfield, product of 2 superfields, product of 3 superfields, product of 4 superfields, chiral superfields. They are all chiral superfields. Now, if I take F term from them, that will also transform under supersymmetry as a total derivative. So, a polynomial W of F, take the F term. Now, this object by construction is a function of x, because you are right. You pick up the D term after expanding y and y bar, and you pick up this is a function of y, because F term of a chiral superfield is the theta square piece, which is a function of y. After you put theta equal to 0 and theta bar equal to 0, that will convert y mu to x mu. So then it will become function of x. But now this is not real. Because it's a chiral product of chiral superfields. Product of chiral superfields are not real. So simply, right, Hermitian conjugate. Is that clear? Hermitian conjugate will be made up of anti-chiral superfields, a polynomial in anti-chiral superfields. Take the F term of that, that's also total derivative under supersymmetric transformation, changes by total derivative. So which means such a, if I take this Lagrangian density, so you write F term of this and F term of this and put finally theta equal to 0, theta bar equal to 0, which will convert y to x and y bar also to x. So this would be most general supersymmetric Lagrangian I can construct with chiral superfields. Now, what is this curly W of phi? curly W of phi is a function of chiral superfields, but not anti-chiral superfields. There's a technical word they use, holomorphic function of phi i's, which means it doesn't depend on phi daggers. It's something similar. So this is what it means. When people use holomorphic, what they mean is it's made up only of chiral superfields, not anti-chiral superfields. And I could write an expansion for that. So since I have this set of phi i's, some constants hi times phi I. This could be a candidate for W, or product of two phi i's, phi I, phi j, Mij, a factor of half just for normalization. Mij has some numbers. Repeated indices are summed. So some over i's, some over ij's. Or I could also add these are the possible terms I can have in W. I could have more also. Now, if I take these three phi's, what is the F term for three phi's? What is the mass dimension of F term of three phi's? He said 4. Does everybody agree with it? It's a coefficient of theta square. Theta square is mass dimension -1. Phi each is mass dimension 1. So 3 plus 1. So it's 4. So this would be mass dimension 4. F term of this object would be mass dimension 4. Is that clear? F time of this object would be mass dimension 3. F term of this object would be mass dimension 2. Mass dimension 2, mass dimension 3, mass dimension 4. Now, if I put product of 4 phi's, what would be the mass dimension of the F term? 5. We don't like to write renormalizable field theories with operators of mass dimension larger than 4. So, if I want renormalizable field theory, this is all for renormalizable field theory. Yes, I want to keep this. Now let me write down, I have written the expansion here. Of general product of two superfields. There I have both 1 and 2 are same. 1, 1 or 2, 2, because I is the same. So I just put F1 equal to F2, 1 and 2 indices equal, and rewrite this. That is the D term for this object. So let me write down now phi dagger yi theta bar phi I y theta. This is what it is. Somewhere I think I have, this should have been bar, right? Now notice these terms, these three terms, they differ by total derivative. Straightforward. So by partial integration, I can convert this into this up to total derivative. This also into this. So therefore, now let me write M is Fi star Fi plus d mu phi I d mu phi I. So dropping total derivative terms. So I drop the total derivative terms and write, so convert this into this, convert this into this will be half, it will change sign, 1 quarter plus 1 quarter, that will half, that will make into 1, and that's the total derivative term which I found. Similarly, these two are equal up to total derivative. You take the derivative, this derivative on that side, which is this term, with a change of sign, and total derivative. This object is nothing but phi I dagger phi I d term, all function of x. Now, next, well, let me write this. Hi plus f term of this. F term of this is Fi. So let me skip a step. F term of this is Fi. So Hi times it. What is the F term of this object? We did this as an exercise. calculating the F term of product of two chiral superfields. And that is this coefficient Mij Fj times Fi. Well, notice Mij's are symmetric. Mij and Gij are symmetric in all their indices. So that is the F term of this product, phi j times Fi. Then we also did the exercise of F term. There is something more in F term of this. There was also a piece in the F term of product of two, which was fermion bilinear. So let me write that one also. Psi I, psi j, Mij. So this plus this is the F term of product of two chiral superfields. Then F term of three chiral superfields is Gij phi j k times Fi plus a fermion piece. So that is the F term of curly W phi plus Hermitian conjugate, and put theta theta bar equal to 0, convert all y bars into x. Now we have written down the most general Lagrangian in 4 dimensions, supersymmetric invariant Lagrangian that we can have in 4 dimensions made up of chiral superfields. Renormalizable. Now let me introduce some symbols. We had W of phi. There's a name given to this, maybe I didn't mention this. This W of curly W of phi. Superpotential. Take first derivative of superpotential with respect to superfield I and call it Wi of phi. Some notation. Take the second derivative with respect to phi I and phi j and call it Wij phi. You can take third derivative also. Now if I take the first derivative, what do I get here? Hi that's my derivative, W, just take the first derivative. Take the second derivative, what do I get? Now, in terms of these, I can rewrite this Lagrangian in a slightly more compact form. So I have d mu phi star minus I psi bar sigma mu d mu psi I plus fi star, this is as it is, plus wi phi of fi minus half psi I psi j of wij of phi plus Hermitian conjugate.
How do you define the derivative of this in respect of
Superfield as an object is a field. The same.
I mean, whose only component is
So as a one object together.
I mean, it's just a symbol for a
But it's a scalar under Lorentz group. So for this differentiation thing, so use the ordinary differentiation rules. So anyway, if you don't want to differentiate, just call Wi to be this object, and that's it. Right? This is a well-defined object, right? Wi. Now this Wi phi and Wij phi, these are written as functions of superfield. Here, this is the lowest component of the superfield. This is ordinary scalar field. Right? The same functional form with superfield replaced by ordinary field. Okay? So that's exactly that's rewriting this. So this is a little more compact. Now clearly in this Lagrangian, phi's are dynamical fields because they have kinetic energy. Fermions are dynamical, they have kinetic energy. F fields don't have any kinetic energy, please Lagrangian. So F cannot be a dynamical field, which is what I have been saying all along. And this is an explicitly construction now. F are non-dynamical, which means they don't have equations of motions with time derivatives in them, but they have equations which control them, which don't have time derivatives in them, which means they're controlled by constraint equations. So let me calculate the Euler-Lagrangian equation associated with the variation of phi. So vary with respect to what do you get from here? You get the equation fi star from this, and from this and if I vary with respect to fi star, you get the conjugate relation. Where bar is complex conjugate. That you will get one from here and from the Hermitian conjugate piece here. So what does this tell us? This tells us that Fi star is omega Wi phi, or Fi is minus Wi phi bar. And Wi is this object. This object. So what does it tell you? It tells you that F is not an independent field, but it is constrained to be a function of the other dynamical fields. Clear? Euler-Lagrange equation of motion is Euler-Lagrange equation of motion. That's not really dynamical equation of motion always. Euler-Lagrange equation is you extremize your action. And Euler-Lagrange equations give you dynamical equations for dynamical fields. For non-dynamical fields, they give you constraint equations. So this is what it tells us, that F is just some function of i's. And in this particular theory, is a function of defined by Wi phi, which is this. So, it's a constraint equation. I can put it back into the Lagrangian and write a new Lagrangian. That doesn't change the dynamics of the Lagrangian. So let me put back that into this Lagrangian. Now before I do that, let me calculate this. Wi phi I plus Wi bar phi I star. That is this term plus Hermitian conjugate term. What do I have here? This object is minus Fi star Fi. This object is minus Fi star, that is minus 2 Fi star. And now let me put here all these terms together, all scalar field terms together with their derivatives. What do I have? And call that minus potential for phi. Potential is defined, this Lagrangian is defined as kinetic energy pieces minus potential energy. So whatever that object is minus V, and that is this object is minus 2 FF star. This object is 1 F star. So that is so V of phi is Fi star, Fi mod square, always positive. non-negative, positive or 0. And this is what we have been saying from the beginning. We said supersymmetry implies non-negative T for energy eigenvalues. So potential has to be non-negative in supersymmetry. That is, should have been expected. And that is in particular the property of this construction of supersymmetry Lagrangian. The potential is always non-negative. Potential is non-negative. So now let me rewrite this Lagrangian. Now this is a supersymmetry Lagrangian without the auxiliary fields. It has only dynamical degrees of freedom. And the potential is non-negative. What does this describe? This describes a set of fermions, psi i's, psi i's, and a scalar field, set of scalar fields, complex scalar fields, phi i's. Now, if you look at what we have, phi i's are, each phi I is 2 real numbers for every value of I. And each psi I is 2 complex numbers. But now, because they have dynamics, we have eliminated F's. We don't have off-shell equality of Bose-Fermi degrees of freedom because we have eliminated F. If we had not eliminated F in this Lagrangian, there is Bose-Fermi equality. 2 complex for each I value in phi, 2 real components in phi, 2 real components in F. So 4 bosonic real components, 4 real components in one side. 2 complex components, that's 4 real components. But now when we have gone on shell, which means we have excluded F from, we'll have only on shell equality of Bose-Fermi degrees of freedom. On shell degrees of freedom of psi I, each psi I, are only 2 real degrees of freedom because Dirac equation takes away 2 degrees of freedom. Is that okay? Let me now simplify this a little bit. Simplify. Let me take W of phi, the superpotential, to be only this much. Take one superfield. instead of the whole set, let me take only one. And let me take superpotential to have a simple form. Half m phi square. And let me write the action. D for x, phi dagger phi, d term plus 1/2 m phi square f term plus Hermitian conjugate. I will not write this theta theta bar. In this you put theta theta bar equal to 0 in the end, so that you write this as a function of x. This by construction is a function of x. And do this exercise that we did earlier. This is the Lagrangian you have. This is the d term of this object. This is the f term of this object. There's no factors of half or anything. Yes. I'm just a simple example. I'm just giving that. That's you've already seen it's a free theory. Now let me use constraint equations. Variation of f and f. Variation of f gives me f star plus m phi is equal to 0, and if you do variation of f star, that will give you f plus m phi star is 0. Put it back here. Like he said, it's a free theory. Free theory containing a fermion and scalar, both of same mass. For scalar theory, m square times phi dagger is the mass term. For fermions, m times psi bar. This is a theory of a complex scalar field and a Majorana spinor, both of same mass. Notice this is the nature of a Majorana mass term. Is everybody happy with that statement? That this is a Majorana mass term? We had said earlier a Dirac field is made up of two chiral fermions, psi alpha, chi bar, alpha dot. in the 4-component notation. And a Majorana field is made up of psi 2 components and conjugate of those 2 components. Where a Dirac field is this object and independent chi's. So that makes 4 independent complex numbers here. In a Majorana field, there are only 2 real independent complex numbers here, because this pair is complex conjugate of that. Dirac mass term you would have seen is psi bar m psi, while psi bar in 4-component notation is psi dagger multiplied by gamma naught. This object written in terms of these components is m psi chi psi bar in the 2-component notation. A Dirac mass term is one 2-component fermion, second 2-component fermion, both in half zero representation, and their complex conjugates in 0 half representation. And this is alpha component summed here, alpha dot here summed here. That is the Dirac mass term in 2-component notation as opposed to 4-component notation. A Majorana mass term is again, you write it the same way, except this was Dirac, but write it in M. Because chi and psi are the same. Is that clear? So this object is a Majorana mass term.
Whenever, instead of taking one superfield, I could have taken a bunch of superfields. As long as the potential has only this term, it will always be a free. What I'm saying.
Yes. If you take only phi square superpotential, so phi square superpotential gives you free theories. Now I want to make one general remark. We have seen that to write supersymmetric Lagrangians or supersymmetric actions, we write it in terms of Lagrangians which change under supersymmetry by total derivative. So you might ask, can I write a Lagrangian which just doesn't change at all? The Lagrangian in a SUSY theory cannot be SUSY invariant on its own. That can never be, except in trivial case when Lagrangian is constant. It has no. It always has to be one that transforms under supersymmetry by a total derivative, so that action is SUSY invariant. And the argument for that is very simple, is that now if I took a Lagrangian density and made two supersymmetric transformations, on it by an amount epsilon 1, then followed by an amount and epsilon 2, and the reverse order, and took this difference on a Lagrangian. Now from supersymmetric algebra, what is this object? Minus I epsilon 1 sigma mu epsilon 2 bar epsilon 2 sigma mu epsilon 1 bar d mu of n. I have sign right? Minus I, right? Because that's what the SUSY algebra is. This object is equal to this d mu. So acting on a Lagrangian, that's what it would be. Now if Lagrangian is supersymmetric invariant, that means delta variation of L is 0 on its own, right? If delta epsilon of L is 0, that means Lagrangian is supersymmetric invariant on its own, then so Lagrangian density will have to be a constant. Is that clear? So Lagrangian can never be on its own supersymmetric invariant. So that's one. Second one, which is a repeat of what we said earlier, is that if you want to make supersymmetric Lagrangians which transform by total derivatives, pick up the d term of SUSY Lagrangians are a d term of phi dagger phi and f terms of a product of chiral superfields. Now, so far we talked about supersymmetric theories which contain only scalar fields and fermions. We did not talk about supersymmetric theories which contain vector fields. Now we'll start a discussion of theories with vector fields. And for that we have to introduce a new superfield, new kind of a superfield. We'll call it a vector superfield. vector superfield. Earlier we introduced chiral superfields, now vector superfields. Vector superfield, give it a symbol V, is one that is real. At the early stages of discussion of superfields, I wrote an expansion of a general superfield in 4 dimensions in terms of various component fields as coefficients of theta-less term, 1 theta, 2 theta, theta bar, thetas, and theta bars, and so on and so forth, up to the term with 2 thetas and 2 theta bars. I can write the same kind of expansion for this, except that there I did not put any reality conditions. That was a general superfield which was not its own conjugate. Now I want a superfield which is its own conjugate. So look at that expression and see that I can expand V. So V is a function of x, theta, and theta bar, and I can expand it in terms of a theta-less object, call it C, C of x. The field C of x. And this would be real. Plus an object which depends on theta, and call that chi of x. A term with single theta and chi. Now chi is fermionic, because theta is fermionic. This together is bosonic. This together is spin 0. Okay, this is not real, but I want a real superfield. So I add theta bar to chi bar. And just normalize it by square root 2. In that superfield that I had constructed, I think I had introduced one symbol for this and one other symbol for this, which were not each other's conjugate, because that would be the most general one. But I want reality now, so those 2 terms will be related. Then I take 2 thetas. And M, the field, I call it M of x. Now this is not real. So to make it real, I add theta bar, mx star. So M is not a real field. M is complex. Again, in general superfield, I had introduced M here and N here, independent ones, but N now would be an M star, because I want a real superfield. Another 2 theta term I can construct is theta sigma mu theta bar. This object is real. So I can multiply by a vector where A mu is real. There A mu was not real when I wrote the most general one. But here A mu is real. Then I could add 3 theta term, theta theta, theta bar, and theta bar, theta, and multiplied by lambda of x and lambda bar of x and lambda of x. They are each other's conjugate. I'll do something for convenience is that define this term with a new field lambda with some additional piece which is a derivative of this chi. I by root 2 sigma bar mu d mu chi of x plus I by root 2 sigma mu d mu chi bar x. That is just a convenient definition. I could have done this much, this was not needed. But a convenient definition is that I add these pieces to that. We'll see what is that convenience. That takes care of 3 thetas, and next is the 4 thetas. Theta, theta, theta bar, and 4 theta we always call a D term, so give a symbol D to it. Now again, this is real, so dx is real. Again, for some convenience, I put up normalization half here and add a piece of half box Cx here. But Cx is the first component of this. This is the most general expansion of a real superfield. And I prescribe mass dimensions to it. Now I prescribe that C is mass dimension 0. So this vector superfield is mass dimension 0. So mass dimension of V is 0. Therefore, mass dimension of this first component is also 0. Then what is the mass dimension of chi? Minus half. Mass dimension of M, 1. M star is also 1, M is complex conjugate. Mass dimension of A mu plus 1. Mass dimension of, then what is the next one? Lambda, right? Lambda 3/2. And mass dimension of D now this choice I have made deliberately because I started, I could have made this any mass dimension. I started with 0 so that A field has the right mass dimension of a 4-dimensional vector field. Is it clear? This A field will be our vector field. And because A field lives in this superfield, we call it a vector superfield.
So only A and lambda can have dynamic.
See, she's already seen the point. Now, the point is that all other fields have some odd, bad dimensions. So all other fields must be auxiliary fields in this multiplier. Now you count the bosonic and fermionic degrees of freedom here. Bosonic degrees of freedom, is it 8? 1 and 2 here is complex, 2 real. So that is 3, 4 here, 7, 1 in D, 8 real. Fermionic 2 complex here, 2 complex here, 4 complex, 8 real. See, the general superfield that we had constructed earlier had 16 for bosonic, 16 for muonic. Now, because of reality condition, each one of them is going half. Now, this is a super multiplet and a complete multiplet made up of these many fields with equal boson Fermi degrees of freedom. It contains a vector superfield and it contains a spin half, mass dimension 3 half field, and it contains a mass dimension 2 field. If you remember, we wrote a super multiplet, vector super multiplet, which was made up only A mu, lambda and D. And then we did off-shell counting and we realized that off-shell counting was not correct. On-shell counting was correct. Off-shell counting was correct. That's because that multiplet that we had constructed was not a complete multiplet, super multiplet. It had many more auxiliary fields than one D field, and that is this one. So now this is a full supersymmetric multiplet containing a vector field with all the auxiliary fields needed for this super multiplet. Is that clear? We'll see soon how to get from this to the reduced super multiplet. To do that, let me construct a chiral superfield. Consider a chiral superfield, and we'll give it a name I times lambda. I is root minus 1. You just carry an I, that's for convenience. Since this is a chiral superfield, I should be able to write it in terms of as a functions of y and theta, and make an expansion of phi theta plus root 2 theta psi y plus theta theta fy. This is chiral superfield, so I can write it like that. Chiral superfield means d alpha on lambda, d bar on lambda is 0. That was our definition of chiral superfield. And we remember y mu was x mu plus I theta sigma mu theta bar. I can make an expansion of this object. We have written this expansion several times. Back around x point, a Taylor expansion, and write down this whole multiplet. That this superfield has functions of x, where components are functions of x. So the answer is yes, that's it. This object, and this object comes from Iy expansion. This object and this comes from this expansion. This comes from there. It cannot have any more term because that will have more than 2 thetas. Now for a chiral superfield I lambda, conjugate of this is an anti-chiral superfield minus I lambda dagger, where d alpha lambda dagger is 0, is an anti-chiral superfield. So I can write a similar expansion for that object, because now this would be a function of y bar and theta bar, and write the same expansion, which would be nothing but a complex conjugate of this object, and then construct, add these two up, construct a superfield. It's in fact a real superfield, which is I lambda minus lambda dagger, which is sum of these two. This is conjugate of that, so this is a self conjugate. This is a self conjugate superfield, so it's a real superfield. This plus this complex conjugate. So that is the theta less term, root 2 theta psi x, theta bar psi bar x, theta theta fx, theta bar f star x, plus I theta sigma mu theta bar d mu phi x, conjugate of this object. This is theta sigma mu theta bar is self conjugate. I changes sign, so difference phi minus phi star, because of this I inserting in front. So this term and its conjugate, it would be minus this and these terms interchanged, but use the identity that you can get it back by changing a sign, and that's what I've done here. Then the last term. Now is that an interesting thing to see is the coefficient of theta sigma theta bar piece. d mu phi minus phi dagger, phi star. A gauge transformation on transformation on a vector field A mu. X as A mu goes to A mu plus D mu xi. Let me rewrite that as A mu goes to I d mu phi minus phi star, call xi to be I times phi minus phi star. Is it clear? Then this object here looks like the change that a gauge field would undergo under gauge transformation. So now, if I add, this is a real multiplet, its own self-conjugate by construction. If I add that to this real multiplet, it will change my A mu by that amount, which means it will implement on A mu a gauge transformation. Clear? So, if I generalize now a gauge transformation on vector fields to gauge transformation on a vector superfield, all I did to do is generalize gauge transformation. On vector superfields by saying that V goes to V plus I lambda minus lambda dagger. Such a thing would implement gauge transformation on A mu and change other fields by whatever procedure it is.
Inner field also have a gauge transformation.
Yes.
So that also you have to.
Yes. Now, spinner field has what transformations? What is the spinner field transformation? Lambda. What is the charge of lambda? When you know abelian generalization, we'll worry about that. Here it's very trivial. Huh? So now, let me see what that means for component fields now. For A mu, I saw what it means. But what does it mean by component fields? Then, under this transformation, C field changes to C plus phi dagger, phi plus phi star. Chi changes to, this chi is the theta component, chi plus theta component is here, psi. M and chi bar similarly to chi bar plus psi bar. So I'm not writing that. M changes to M plus F. And A mu changes by now this combination changes by this plus right, but psi changes by psi, so chi changes by chi plus psi. So that means this change is change of this piece, because we prescribed how chi changes. Chi changes by chi plus psi. So this chi will change by chi plus psi by adding this piece. That will leave lambda unchanged. Now you know why that convenient piece we added here. If we had not added this piece, then we would have to change, lambda would change in a particular way, and then we do some other exercise, define another lambda, which would stay invariant, right? So we did this clever thing by putting it right there. So that lambda so defined does not change now. What happens to D? So D changes to D, and then there is an extra piece here, box of phi star. But that is exactly the change of box of C. I have the number right? 1 by 4, 1, is this number right? 1/2. Huh? There's a half outside here. So that takes care of C. So D does not change. That's another reason why we put that object conveniently here. Now under supersymmetry transformations, under gauge transformations, C changes in this way, chi changes in this way, M changes in this way, A changes in this way, lambda and D don't change. Now I can use this to eliminate some fields from the theory. So let me construct a lambda which will take away C0, make C0, because I choose phi star to be equal to be minus C. So you make C to 0, you can make chi to be 0, you can make M to be 0, and this would be simply a gauge transformation of A mu. You will be left with A mu, lambda and D. Gauge choice. This is also called Wess-Zumino gauge. Use this definition of gauge transformation and put C to be 0, chi to be 0, M to be 0, and you are left with then, we are left with A mu, lambda and D. The general vector field we constructed had 8 bosonic real degrees of freedom and 8 fermionic. Now we have thrown out this is 3 real bosonic, 1 here and 2 here, and 2 4 real fermionic. By gauge choice, we have thrown away 3 bosonic degrees of freedom and 4 fermionic degrees of freedom. And we are left with 4 and 1, 5 bosonic and 4 real fermionic. This is not Bose-Fermi equality. There is no Bose-Fermi equality. That's because of gauge choice. If you want to give Bose-Fermi equality, then you keep all these objects. And if you keep all these objects and then set up supersymmetry transformations on them, you will realize supersymmetry algebra closes without any use of extra gauge transformations. See, when we did this supersymmetry vector multiplet, we realized gauge transformations close only up, supersymmetry transformation algebra closes only up to a gauge transformation. That's because we were working in a particular gauge fixed version of the theory. I think you made a remark about I'm gauge fixing it. And that's it. Yes, we were in a gauge fixed version. But if I did the same now with the full set of superfields, I would not need any extra gauge transformation for closure of supersymmetry algebra. Now, in this gauge choice, let me write down the vector superfield, and we'll stop at that today. What does M star is F star, and the complex conjugate of that, right? So I didn't write that. Okay? Said it?
You have to put it.
If I put M to be 0, complex conjugate of MD is also 0, right? M equal to 0 is both real and complex parts of M are 0. Theta sigma mu theta bar A mu of x plus theta square theta bar lambda of x plus theta bar square theta bar lambda x plus half d square d bar square of d of x. This is this vector superfield in Wess-Zumino gauge. In Wess-Zumino gauge. So we'll stop at that.